Okay, so now we'll finish off this set of notes by talking about some inferences that we can do in logistic regression. So inferences about the model parameters. And remember, inferences typically means hypothesis testing and confidence intervals. So we can do hypothesis tests and confidence intervals about the betas. And I just note here that the interpretation of logistic regression is quite a bit different from linear regression. We're not talking about means anymore. We're talking about probabilities. But the inferences that we would make are actually going to be very similar. The main difference, if you remember, in simple linear regression, we used students' t-test statistics or just t-tests to evaluate the model parameters. In logistic regression, we're going to use z-tests, or they're called WAD z-tests, and they're really based on z-scores, from which p-values can be determined from standard normal distributions. And remember that standard normal means mean 0, standard deviation 1. With the main assumption being that we have a reasonably large sample, and we'll talk more about that soon. So the general form, so remember that the general form for many test statistics is equal to the estimate minus the null value divided by the standard error of the estimate. This is the same thing you saw before. But it turns out, so this is the same formula that we saw for the t-tests in linear regression. But it turns out that for logistic regression, this calculation, if the sample size is big enough, this calculation will follow a z distribution, a standard normal distribution, rather than a t distribution. But you see it's the same calculation that we saw before. Beta 1 hat minus 0 is typically the null value divided by its standard error. And again, this is a function, not a multiplication, right? This is the standard error. And a standard normal distribution looks a lot like a t distribution, and you probably saw this in Stats 212. And 0 is at the middle because the mean of a standard normal distribution is always 0. So it looks a lot like a t distribution. As you'll see in SAS, and R actually does this as well, most statistics packages actually report a chi-squared test statistic instead of the z statistic. But it turns out that the chi-squared distribution with 1 degree of freedom is really just the same as squaring the z statistic, and they'll produce an identical p-value. So z squared, z is, again, the estimate minus the null value divided by the standard error of the test, is equal to a chi-squared distribution with 1 degree of freedom, a chi-squared statistic. So going back to our table, what did we see here before? So notice that SAS gives you chi-squared test statistics. What this actually is if z is equal to 3.1186 minus the null value is always 0 for these test statistics, so you can just plug 0 in, divided by its standard error, 1.3337. If we square that, you'll get 5.4673. And similarly, this is negative 0.1514 minus 0 over 0.0823 squared. And the p-values correspond to the chi-square statistic. But these are the exact same p-values that you would get if we used the standard normal distribution. Okay. Which I think I'll show you here. Nope, I guess I don't show you that. That's fine, I'm not going to ask you to do that. So now let's talk about confidence intervals for the model parameters. So we can do a hypothesis test for the model parameters. And of course, they're provided automatically by SAS. Or we can do confidence intervals. So just as with the test statistics, the confidence intervals look a lot like what we did in simple linear regression. And again, one of the main assumptions is that we have a big enough sample, and I'll talk about what I mean by that in the next set of notes, I believe. But our confidence interval is simply beta 1 hat plus or minus, instead of a t now we have a z. And it turns out this is a little bit easier than working with the t because we don't have to worry about degrees of freedom. The z-scores will always be the same. Okay? So it's beta 1 hat plus or minus a z times the standard error. So z, as I say, is an appropriate quantile from the standard normal distribution. And here are some of the commonly used ones. Of course, if you want a 95% CI, confidence interval, that means alpha is equal to 0.05, so we'd use 1.96 as kind of the magic number. But we can also ask for 90% confidence intervals, in which case we'd use 1.645 for Z in our formula. And we could also ask for 99% confidence intervals, in which case we'd use 2.58. So as an example, calculate by hand a 95% confidence interval for beta 1 in the model for age and sleep above. Recall that, so beta 1 hat is negative 0.1514, and the standard error is 0.0823. So if I want a 95% confidence interval, 1.96 comes from that table. So there's negative 1.514 is our beta 1 hat, plus or minus 1.96 times 0.0823. If I calculate that out, I'll get negative 3.127 to 0.0099. Now, we can ask for SAS to give us that, and of course the notation is slightly different than we saw. It's similar to ProcGLM, but we have to add one extra thing. We want to say that CL parm equals WAD. And if I do that, I already have my SAS program up here. If I just add that to the end of my model statement, CL parm equals WAD, not walk. You'll notice that I get parameter estimates and WAD confidence intervals. So it's not in the table of maximum likelihood estimates, it's down below here, parameter estimates and WAD confidence intervals. So my WAD confidence interval for age, for the slope of age, negative 3.128 to 0.0100, that's without rounding. My rounded version is just slightly off from that, but you'll notice that's the same, essentially the same confidence interval. We can also do confidence intervals for odds ratios. Remember that one thing that we might want to estimate from a logistic regression model is an odds ratio. So the odds ratio is estimated by exponentiating the parameter estimates. So we exponentiate beta 1 to get the odds ratio for a 1 unit increase in age in this sense, in this example. We can easily compute a confidence interval for the odds ratio simply by exponentiating the limits of the interval for beta 1. So our interval for beta 1 is calculated using this formula. The interval for the odds ratio would just be the exponential of beta 1 hat minus z times the standard error, and the upper limit would beta 1 exponential of beta 1 hat plus. So we have the minus and the plus. Right? So I can calculate a 95% confidence interval for the odds of getting 7 hours of sleep associated with each additional year of age. So remember that the confidence interval for each additional year of age, or for the slope for each additional year of age, was negative 0.31 to 0.0099. I can exponentiate both sides of that to get 0.7315, that's e to the minus 0.3127, and e to the 0.0099 is 1.0099. And it turns out that Proclogistic gives us these odds ratios and confidence intervals for free. And here's the table of odds ratios estimates. There's age. The point estimate for the odds ratio is 0.86, and the confidence interval 0.731, 1.010 is essentially what we calculated up above. So now let's interpret this interval. We can say that we are 95% confident that the true odds ratio relating age to getting at least 7 hours of sleep on average, of course, is between 0.731 and 1.010. So we're 95% confident that the true odds ratio relating age to getting at least 7 hours of sleep is between 0.731 and 1.010. Now remember, we're talking here about odds ratios. So since we're talking about ratios, a ratio of 1 indicates no difference. So an odds ratio of 1 here would indicate that age does not increase the probability of getting at least 7 hours of sleep. So because 1 is inside this interval, we have insufficient evidence for a relationship at the 5% significance level. So, and just recall that our p-value was, if we look back at the table, the p-value on the slope was 0.0661, which is not less than 0.05. So if we're talking about the 5% level, 5% significance level, this value is not less than 0.05. And so our confidence interval relates to directly to our p-value. So the p-value is not significant at the 5% level. The confidence interval for the odds ratio includes 1, just barely. The p-value is just barely above 0.05, so those correspond. And if we look back at the confidence interval for beta itself, that confidence interval barely includes 0, right? We have a negative side and a positive side, just barely positive. So all of these inferences align with one another. And we'll talk a lot more about inferences moving forward.